Welcome to SanfordFlipMath. This is AP Calculus, and we are working on a review session for Finney, Demana, Kennedy for 7.1 through 7.3, and I have silly people in the room. How can I do a shout out to everybody all at once? Yeah, all right. So Nakaya, Jeff, Steve, Alex, but not Alex. Yeah, Alex Foster. Kiera, Justice, Austin, Michael, Kiki, Micaiah again, and Darnell. All right, that's everybody. And the rest of y'all, where are you? All right, so the request has already been made that we're going to look at number one. We're going to start at number one. How shocking, from the practice test for 7.1 through, it's really 7.3. I'm going to pause while. All right, late shout out for late Nia. All right, so we are going to do, we're supposed to find displacement over the first 3 seconds. Remember, displacement is really just the net change in distance. It is not the total distance we've traveled. It is just the difference between where we started and where we end up. So if we start here, and then maybe we go here and we come back and we go back and forth 27 times, and then we end here, displacement is really just that distance, not all of that distance. Okay, so for displacement, honestly, all you need to do is the integral for, it said the first 3 seconds and it's specified from 0 to 3, just to clarify. Just take the velocity function and do the integral, and honestly, that's it. Okay, so that's the setup. Calculator can be active for this problem. Make sure you're in radian mode, type, done. If you feel compelled to do it analytically, then you're welcome to do that as well, or if it was a problem that said you had to, that's fine. Antiderivative of sine is negative cosine, and you got to do it over 3. Can I leave it at that? Yeah, sure. All right, so that's it. You can type, I'll leave it at that. Okay. Total distance. Okay, so now again, if I have that start and I start going back and forth, I need to count all of that. Okay, so the idea again is if I take the long way around, you know, I'm going around Lasser Road to 9 Mile to Telegraph to 10 Mile and back to the school again, you know, maybe my displacement is 10 feet, but how far did I go? I might have gone 4 miles to get there. So total distance is total distance. Well, if I do a little graphing of this just to kind of get a feel for what's going on, it's going to look something like this, and let's see, the period's about 1, isn't it? Well, it's, oh no, it's about 2. Period would be 2 pi over b. Not that I mean, you can graph this in your calculator, but this is going to be 6.28-ish divided by 3, so about 2. So the only reason I'm doing that is this is 2-ish. There are going to be some different parts to this graph over the first 3 seconds. So here I am, the first, so somewhere around here, and I don't know where it is, but there's a positive part of this graph, a negative part of this graph, and a positive part of this graph. So the idea is like this is going forward, this is going backward, this is going forward. And all of that needs to become positive. Well, the easiest way to make that positive is if I just do absolute value. So I could do all of this by just saying, okay, let's do the absolute value of 5 sine of 3t dt. And now the graph looks like this kind of thing. And so all of that distance becomes positive, and I don't really have to work that hard. Now, if I was going to do this by hand, I would actually have to split this up into little chunks. I'd have to find that point where it really does cross, and do an integral from 0 to that number, plus, and I'd make an absolute value of this, and you know, it'd be a little more work. But if I'm going to do this in the calculator, then I can just make it absolute value. All right, so the request was, can we do this in the calculator so we can actually see what's going on? Let me go back over here. Are we talking about displacement? The total distance, the absolute value. All right. No. Well, maybe. Well, this software is all set up with the new system, so I don't know if I can. I'll put it in classic mode, and we'll see if it'll show it or not. I don't know. We'll see. All right. So let me insert. I'm going to do second delete, so it's inserting absolute value. Now, I can get absolute value by doing second in catalog, or I can go into math under number. Okay, and Malik. All right, so, thank you. Hello, what happened? All right, not what I wanted. Second catalog, absolute value. There it is. Okay, so, yeah, and this looks right. Okay, and I'm just going to close parentheses just to have it complete. All right, so we're looking at part B. This is the total distance problem. And I'm going to start with just, I don't know what kind of window I got going. Yeah, it's not a helpful one, that's for sure. All right, be done already. I don't really know what the window needs to be. I know I'm starting at 0 seconds, and I'm going 0 to 3, so I guess that'll work. That's not a 3. That's a 3. And I know my amplitude is going up to 5 or so, so I'm going to go to 6 just so I go a little bit farther. Okay, so this is what we should be looking at. Now, again, if I'm going to do this with absolute value in the calculator, and Courtney Ray. Woo! Woo! All right. So since we're doing this in the calculator in this view, is it okay if we do this with the integral on the graph? So in other words, I'm going to go to second calculate, and I'm going to do 7, and I'm going to start from 0, and I'm going to go to 3, and it should start shading for me, and it might take a bit. I don't know. Looks like it's going to take a long time. Oh, here we go. Not bad. All right, there you go, 9.852. And that's the total distance. That's B. 9.852. Like that? Yep. It'll be on YouTube. All right. So yeah, just a quick recap. What just happened was I went to second and calculate, and I did the integral. And I started at x equals 0, and I went to x equals 3 since x is replacing my time. Instead of t, it's x. Okay, and I don't know what just happened. Is it doing it? Oh, I didn't? Oh, stinky poo. I just stinky pooed on a recording. That's nice. 0, 3. Okay, and it would be shading this as it was going along, but it was already shaded, so that's why it's doing this. It's thinking. There you go. Okay, and you could do this through the Math 9 also. I mean, it would work the same way. The only issue is that you got stuff to type in, right? So yeah, this is the old system setup. Okay, all right. So if I want to do absolute value of 5 sine of 3. Now you can use whatever you want in this, but I'm going to use x because it's just easy, it's convenient. Okay, with respect to, oh, I didn't close it for absolute value, thank you. Okay, so I closed it for the 3x, I closed it for the absolute value now, cool. With respect to x, from 0 to 3, and again, this is the old system style, so if you're on an 83 or an 84 that's not updated yet, this will work. You have to connect it to the computer. It's kind of a pain in the cheekage. All right, so yeah, that's going to be on recording. Yeah. Southfield teachers suspended. We're talking about. All right. Could have been profanity. That would have been worse. So, yeah, I don't really do that. So, no, we don't. No, we don't. All right, just a quick note about number 4, and then we're going to go to number 5. Bounded by y equals 2x, y equals 6, x equals 0. So here's y equals 2x, y equals 6, and then x equals 0 is this. Okay, so this is enclosing a specific region. Okay, so that region is right here. And then it says rotated around the x-axis. Okay, so what I've been recommending is start by making sure you have the region pretty solid, and then whatever you're going to rotate around, so we're going to rotate around the x-axis, do a reflection across it first. So it's going to look something like this, right, with our little red stuff filled in, whatever. And then try and do the little circle-y stuff to make it look like it rotated. So you could either use shell or you could use washer. It's entirely up to you. You have to make a decision. Now, and that's the tricky thing, okay, is making that decision. I don't know. Depending on what mood I was in that day. Because I think this one is pretty straightforward either way. So that's that. So if you're looking for an example to try and do both ways, so you're sure you understand something, that's actually this would be a good method or a good example to do that with. So I don't know. Do you have a preference? Washer. All right. Kiki talked first. All right. So if we do washer method, now here's the idea: is I have this. Here I have a disk with a hole in it. Okay, so if I take that circle-y looking thing, it's got a hole in it, and so like this part's that red stuff, right? And so now the idea is that I have a bit. Now remember, the radius is always from the rotation. It's from the center. In this case, it's from the x-axis. It's not always from the x-axis. It depends on what they say. Okay, so the they in this case was me. But it's rotated around the x-axis. So I'm going to measure there's a big radius, and that's all the way from here up to here. And my question is that radius changing? So the distance from here to here is 6, the distance from here to here is 6, the distance from here to here is 6, and that y value is staying 6 for the big radius, right? The setup for this that we've talked about is this idea, and then this is going to be either dx or dy depending on what direction we're going. Okay. Well, in this case, okay, so this is the volume. In this case, that big R is staying the same. So it's going to be 6 squared minus, and then the little radius is this distance, and is this distance staying the same? No, it's not, but it is a y value. It is really, isn't it just that? It's following this line, which was this. Isn't it just the y value, the y value, the y value? See, I'm talking about the actual radius. I'm not talking about how thick this is from here to here. I'm talking about the radius from where it's rotating. Okay, yeah, go ahead.
So, when you find in the first, like the big R, it's from the whole circle?
It's for it's the outside, it's the big radius, it's the big circle. So from wherever you are rotating from, in this case the x-axis, it's the outer one, it's the big circle. It's from the center all the way to the outside. That's big R. And then the little r is the little one. Is for the whole. Remember, the whole idea is with this thing is that it's like some kind of a weird cone dish. The outside looks like a cylinder, and then the inside is hollow, like a dog dish or something that you'd put water in or food in or something. Only it's a cone on the inside. Okay. Yeah.
So how would you know the difference between, like, this is just 6, but how would you know if it's like 6 minus x?
Well, the issue is about where are you rotating around. So like we've seen some where like maybe the rotation is here, you know, and so we're going around like this. And so the radius in this case would be from here over, I don't know, let's say that's 6. And so this would be an x value, and then this radius would be 6 minus x. Right? So it's totally about where are you measuring from. Right, whatever this y value is, it's measured straight from this x-axis. That's what we're rotating around. It makes it an easier problem. When you start rotating around places other than the x-axis or the y-axis, that's where things get more, I'll say interesting, and really I mean harder. Okay? All right, so the inside hole is, now this is getting to be a pretty darn busy drawing, and I don't know how to fix it without starting over. Okay, so the idea is that the inside radius, this part we have to subtract out, is just the y value, and that y value comes from this equation. So it's just going to be 2x squared. Okay, and then what's the thickness of each washer? It's dx because it's a thickness this way. So it's dx. So this is the setup. Pardon? Because it's the thickness horizontally. Right? It's a slice horizontally. It has a little thickness to it. So it's a dx. Okay, and at this point, it's just, one other issue before I'm done. What's missing from this setup? The limits of integration. All right, so I'm going from, now I have to talk about x values now. I have to talk about x values. So from 0 to, I think it was 2, yeah. No, what is it? It's really wherever this thing happens, right? So where does 2x and 6 have to equal each other? 3. So this is really at 3, 6. So this goes from 0 to 3. Okay? And at this point, this is really just a basic antiderivative. I'm not going to do the whole thing, but you get the idea. I'm going to simplify it a little bit just for those of you watching at home. So you can do an antiderivative of 36 is 36x. An antiderivative of 4x squared is 4x cubed over 3, and then plug in the 3 and the 0 and all that stuff. Or you could just do it in your calculator. Okay? Since we're going to do calculators on this test, it's not a big deal. Okay? All right. Okay, so for not doing number 4, I think we spent a lot of time on number 4. All right, well, we need to do something from the 5 through 9 bank, and, well, yeah, we're going to do 5 through 9 in the next 8 minutes, 13 at the most, right? Sure. 6 or 7, yep. All right. Okay, so let me, all right, here we go. So number 7 says we're going to find the volume of the solid resulting by rotating the area bounded by x squared, negative x plus 2, and y equals 0 around the y-axis. Let's do a little sketch of this. So y equals x squared looks like this. Negative x plus 2 looks like this. And y equals 0 looks like this. So the first question is, what's the region that we're spinning around? Now, is it this? Then if it is, then why are we talking about the y equals 0 at all? Because y equals 0 is not a boundary for that. Yeah, sorry. So it's actually this little triangular looking thing right here. It's not a triangle, but it's triangular-ish. Yeah, if it was a triangle, that would be nice. Yeah, but it's not. And why isn't it?
Because of the
Yeah, it's got the parabola. Nice job, Nikaya. Around the y-axis. Or if you're having a hard time with my handwriting here, you can, of course, look at the page it came from. All right, shout out to Steve. All right. All right. We're spinning around the y-axis. Okay, just for the record, this is not the y-axis. It's this vertical-ish looking one. Okay, so again, what my recommendation is do a reflection first, and then try and work out where the spinach happens. Okay, so something like this. Okay, so we're doing 7. Now, if you do disk, it's going to be washer because it has a hole in the middle, but I mean, it's the same concept. So we're talking about pi times who knows what. The outer radius, wouldn't that come from this thing? And this guy right here is the negative x plus 2. So again, this is the setup we're following. Okay, so this is going to be pi times big radius squared minus, okay, the little radius isn't that little radius coming from
X squared.
x squared? So the parabola, look, or as we heard, parabola. Now, here's a little bit of an issue I have before we keep writing all this stuff that's wrong. Yeah, it's really not this at all. Can I just back up? Sorry about everybody taking notes because I didn't catch it until just a minute. Yeah, I know. Go ahead and grunt and groan. Okay, just want to be on the video. Yeah, shockingly enough, that'd be on the audio. But ooh, all right. Isn't this really the x? Isn't this really the x value? So that's really x, and isn't this other radius really the x value? And here's the problem. How do I distinguish between big X and little x? That'd be one way. Okay, so quick little note that maybe will help you. What's the thickness of these little slices? It's dy. So these really need to be about y, don't they? All right. So the thickness of each disk is a y value, is a dy rather. Okay, so this is dy. So one of these equations was y equals x squared. So x equals the square root of y. Was that little x or big X? You just want to be on the video. All right, so if I solve this one for x, now there are half a dozen ways to do it. I'm actually going to add x to both sides and then subtract y from both sides. So ultimately what I end up with is negative y plus 2, or if you'd rather, 2 minus y. So all I'm doing is the radius was an x value, and I don't want to write x because this is about y. And I didn't have a way to distinguish between the x's anyway. Okay, the only thing I need to do to complete the setup is again my what? Limits of integration. Now, what kind of values do the limits of integration have to be this time? They have to be y values because everything in here is about y. So from this y value to this y value, which happened to be 0 to 1. Nice job, Kiki. Yep. All right, so this is the setup. We'll leave whatever else you want to do with that to another time. All right, so the issue now is number 8. I don't care. We got like 1 minute. Well, 3 minutes. Just do one. Pick one. We'll be here all day. All right. I'm going back to the same graph. Me too. Y equals negative 2. Okay, now here comes this sneaky thing. If I'm going to rotate around this line, don't I have to be the same distance away from it on both sides? You know, it's just like, and I've said this example to a lot of people, it's like the wheel on your car. You know, hello. I guess we're having an announcement. Okay, for those watching at home, dress down day tomorrow, $2 Tuesday. All right, so doesn't the distance that your tire is from the wheel or from the axle have to be the same on both sides? Okay, so same idea here. If I'm going to count 2 to here, then I've got to count 2 to here. Same idea, 2 to here, 2 to here. And then this is really 1, 2, 3. So it's 1, 2, 3. Okay, so this is, the idea then is it's spinning. You can do whatever method you want. Yeah, this would be a good one to do shell. No. All right, so quick little note. All right, so what we're going to do is actually, I'd like to do one shell method just so we have one that's shell method. And the idea here is that I have some kind of a cylinder kind of thing going on here that I'm going to unroll. Bye, Malik. And shout out to Lance, who wasn't even in here. All right, so whatever. All right, so I'm going to unroll that. Now, what we have going here is I need to say something about this radius. Well, the radius always has to start at the center and go to wherever we are. Well, this is going to be 2 for that part because it's down here at y equals -2, plus this is whatever y is. Okay, so I'm just going to say the radius then is 2 plus y. And the circumference is always 2 pi times the radius. So 2 pi times 2 plus y. Okay, now the height of this little cylinder label-y looking shell thing, okay, that's the technical term for it, shell looking thing, is going to be whatever that distance is. Well, this distance is actually this x value minus this x value. And I know we already kind of played around with this a minute ago, but remember this came from y equals -x plus 2. So 2 minus y, that's what this is. X equals 2 minus y. And then the other one was x equals the square root of y. Okay, so the bigger distance is the 2 minus y, minus the shorter x value is the square root of y. And so the shell method, if you recall, is basically we're going to add up all of the length times width times thickness of this thing. So it's going to be 2 pi 2 plus y times 2 minus y minus the square root of y, I don't really need the extra parentheses, times the thickness of this label. And since this has a thickness this way, that's going to be dy. Okay, and then the only other thing that we have to consider ourselves with is, remember, the substance of this thing starts at y equals 0 and ends at y equals 1. This is the setup. This is a lot of stuff to type in. Now, keep in mind on your calculator doesn't know whether you're talking about x, y, z, q, or p. It doesn't really care. So if you're typing this in and you want to type in these y values or these y letters as x's, that's fine. It doesn't matter. Just know that the setup needs to be correct with the correct letter. Okay, that's doing that problem with shells. All right, so the request is, how do we type that in the calculator? So I'm going to switch over to the calculator, and let's get back to a normal screen. Okay, and I'm going to go ahead and just type it in with the function integral, like with the math 9 thing. So I'm going to push math and then 9. And this will work on 83 or 84 old system. It looks like this. So you type in the equation first. So 2 pi parentheses 2 plus, and you can type a y if you want. I'm not going to. So I'm just going to type x just so I don't have to work so hard. Times 2 minus the square root. Okay, now I need to close the square root. I need to close that factor of multiplication. Don't type any extras though, or it'll yell at you. Comma with respect to x. So if you would have typed y's and did with respect to y, it would work fine. Comma 0, comma 1. Okay, because we're going from 0 to 1. Close parentheses, hit enter, and hopefully this will be wonder bar. It's got to work. So 12.147 something something something. What's this little problem? Okay, so 12.147 something something something. Okay, so 12.14749. That's with pi and everything all in there. And that was shell method. Okay. All right, so I did one with shell, I did a couple with washers, and we talked a little bit about displacement and total distance. I'm going to wrap it up for this video, which is already a half hour. And watch what you want, don't watch what you don't want to watch, and we'll call it good. See you in class. Bye.